So now let's look at L'Hopital's rule. I guess before we get started, L'Hopital, this is the name of the Marquis de L'Hopital. He's not the man that came up with the rule. That was Johann or John Bernoulli, but he did have it published in his book. I guess if you're rich, you can have things named after you. So it's actually a very useful rule for limits. And what we have is this. If one of these cases is true, in the limit as x approaches c of a rational function f of x divided by g of x. This is the type of problem that L'Hopital's rule will be applied to, or problems where I can rewrite it like this. We'll see that in the next video. Something happens here where either the limit as x approaches c of f of x equals 0, and the limit as x approaches c of g of x equals 0, or the limit as x approaches c of f of x is some infinity. I'll put it as plus or minus infinity, but it's f approaches positive infinity or negative infinity, and the limit as x approaches c of not f of x, g of x is also some infinity, and the limit as x approaches c of f prime of x divided by g prime of x exists. So I need one of these and the limit of the derivatives to exist. Then the limit as x approaches c of f of x divided by g of x is equal to the limit as x approaches c of f prime of x divided by g prime of x. So this right here is sort of the rule you need to remember, so long as the numerator and denominator both approach 0, or the numerator and denominator both approach positive or negative infinity. A slight important thing to notice is we are also saying that this exists. If this does not exist, it may be possible that the limit of f over g still exists. We might see an example where that can happen in the next video as well. Basically, for simple cases, it's not a problem. For cases where I try to rewrite functions as this, it can sometimes be an issue. Before we go into some examples, let's talk briefly about why L'Hopital's rule works. And I guess I should say, sometimes there's an S put in here, L'Hopital with the S or without the S. Some of my students like calling it L Hospital's rule. As long as you understand it, that's what's really important. I like to look at it like this. So if we have some axes, and I have a c value, that target x value, and we'll say that the limit of f is 0 at c, and the limit of g is 0 at c. Clearly we can't do 0 divided by 0, okay? But as x approaches c of f of x divided by g of x, we recall that limits never care what actually happens at this target x value, so I just care what's near it, and so I can go to some point a little bit to the right or left, and since they're differentiable, notice I drew what looked like line segments. When I zoom in far enough, they will be locally linear because I can take these derivatives. So this height here and this height here will be in the proportion of f prime over g prime, because I can sort of take a step over and up the slopes of what looks like lines here. So you can see that, okay, it would make sense that this might be the limit as x approaches c of f prime of x divided by g prime of x. Now, full-on proof would be much more difficult, and this only considers the case where both of these were approaching 0, but that's the basic idea. So let's see one example to begin with. Evaluate the limit as alpha approaches 1 of the natural log of alpha divided by 2 minus 2 alpha. And I see here the natural log of 1 is 0, so the numerator is approaching 0. I need to check that. 2 minus 2 times 1 is 0, so the denominator is approaching 0. Now that I see I have a case where it's 0 over 0, I know that I can take the derivative, so this must equal the limit as alpha approaches 1 of the derivative of the natural log is 1 over alpha. The derivative of 2 minus 2 alpha is negative 2. And you should always clean up the algebra each step. In this case, you can see it'll work out either way, but sometimes you might get stuck going further and further and never finish off if you don't just do the algebra. So when I clean up this algebra, I saw the limit as alpha approaches 1 of, this will be negative 1 over 2 alpha. When I divide, it's the same as multiplying into the denominator, or dividing by negative 2 is the same as multiplying by negative 1/2. That's how we get here. Now when I put 1 in for alpha, because this is continuous, near alpha equals 1, I see that I get negative 1/2. And that is the limit of the natural log of alpha divided by 2 minus 2 alpha as alpha approaches 1. Before we go into some other examples, let's consider what happens when we're dividing by things approaching 0 or things approaching infinity. Now I'm going to use some really bad notation here, but I think it's good to see what we have. So if I have a case where I'm approaching 0 over 0, or some form of infinity over some form of infinity, then we can continue using L'Hopital's rule. But what happens when I don't have one of these cases? Well, there's some that should be pretty obvious. So 0 over some number, and I'll say n is not equal to 0. Or 0 divided by some form of infinity. Well, this is clearly the limit equals 0. 0 divided by some number or some extremely large number, the limit will equal 0. But what if I have the 0 in the denominator? And this is where things get a little bit tricky. So if we have n over 0, where n is not equal to 0, or some form of infinity over 0, what's important is this can be one of three things. I can either get positive infinity, I can get a negative infinity, or I can get a dne. And the dne really occurs, it really depends what happens with the 0. So if I'm only approaching in the denominator, that's not how you spell it. Hopefully I spelled that correctly. If I'm approaching 0 from one side, either from the positive side or the negative side, then I'm going to end up with one of these two. However, if I'm approaching 0 from both sides, then I'll get a dne, because let's just consider if I had 5 divided by this 0. As I approach from the negative side, this will be going to negative infinity. And as I approach from the positive side, this will go to positive infinity. So if I'm counting 0 from both sides, then I get a dne case. So let's see this in action. First thing, I don't like this negative exponent. It doesn't look like the other problems, but when I rewrite the negative exponent, I get the limit as x is approaching infinity of x squared divided by 2 to the x. When I see that x is approaching infinity, I can tell that, okay, the numerator is approaching infinity, a positive infinity, the denominator is approaching a positive infinity, and I can use L'Hopital's rule. So that gets me to the limit as x approaches infinity of 2x divided by 2 to the x natural log of 2. That's the derivative of 2 to the x. And when I put in infinity, or when I see what's happening when x approaches infinity, the numerator approaches infinity, the denominator approaches infinity. Let me use different colors there so it stands out a little nicer. And so I can see, it didn't seem to help. But I can do L'Hopital's rule again and get the limit as x approaches infinity. That was like an 8. The derivative of 2x is 2. The derivative of 2 to the x natural log of 2 is 2 to the x times the natural log of 2 squared. So this is just a constant. Every time I take a derivative of 2 to the x, I get another natural log of 2 multiplied in. Now I can see, okay, the numerator is just approaching 2. It's a constant. The denominator is still approaching infinity. And this gets me the case where 2 divided by infinity, 2 divided by an exceedingly large number, is going to be 0. Now let's look at the case where we have that other thing where the denominator is 0 and I got to figure out what's happening. And this can be very tricky with just doing it by hand. I'll do a quick sketch of what this will look like shortly, but here's the idea. So I put in 0. Cosine of 0 is 1. 1 minus 1 is 0. So this is approaching 0. I put in 0. 0 cubed is 0. It approaches 0 over 0, which means I can take the derivative of the numerator and denominator, and I have the limit as x approaches 0 of, the derivative of this is positive sine of x. The derivative of the denominator is 3x squared. And I check again. Well, as x approaches 0, sine of x approaches 0, and 3x squared approaches 0. So I can take the derivative again and get the limit as x approaches 0 of, the derivative of sine is cosine. The derivative of 3x squared is 6x. And now we get into this problem here. So cosine of x is approaching 1. But 6x is approaching 0. Since this is 6x to the first power, an odd power, and this is just approaching 0 from the left and from the right. As we approach from the left, so let's say a very small magnitude negative number, negative 0.001, this will be a negative number here, and I'll get something that's going towards negative infinity. However, as I approach it from the right, a very small positive number, let's say 0.001, this will be 0.006, and 1 divided by 0.006 is an exceedingly large number. It'll be approaching positive infinity. So I can even try to use that notation. I was sort of approaching this from the left and the right. Because of this, this does not exist, and actually causes this up here to not exist. And we could see this if we looked at the graph. The graph of this is going to look, give me a second to get this correct. The graph of this is going to look like the following. It's going to have something going up towards positive infinity on this side and going towards negative infinity on that side. And you can see, okay, as we approach 0, it does not exist. I'm approaching both infinities. Last example is this. So, only difference between the previous example and this example is the x cubed is now an x to the 4th, and that's going to change a lot. So, I start off the same way. The numerator is approaching 0, denominator is approaching 0. I do L'Hopital's rule, and I get the limit as x approaches 0 of sine of x divided by 4x cubed. I see that when I put in 0, this is still approaching 0, this is still approaching 0. And I can do the derivative and get the limit as x approaches 0 of cosine of x divided by 12x squared. And now it looks very similar as I approach 0. This approaches 1. And this approaches 0. But now there's a big difference. Since this is an even power here, this only approaches 1 from the right side. And so 1 divided by 0, well, either way it's going to go towards an infinity, but since this always approaches 0 from the positive side, this will actually equal positive infinity. The difference in the graph is that from both the right and the left, it's going to be pointing upward. I hope that helped out. I'll put up a video next about some of the special cases where when I do things like 0 times infinity or 1 times infinity or many of these other, not 1 times infinity, other cases where it doesn't look like a fraction to begin with, but L'Hopital's rule can still evaluate the limit. If you have questions, comment below.